Hey guys, welcome to 10.3, and in this video we're going to be learning about how to determine what a limiting reactant is and an excess reactant. As you can probably tell from the title, we're going to be learning about which reactants will limit our reaction from like actually working, and what reactants will we end up having like extra of. In a real world, we have the exact amount of reactants to produce a certain amount of product, but life's not perfect, right? You run out of milk for your cereal. You run out of wood for a fire. There's no bread left for your sandwich. Okay? So in an ideal reaction, we have the exact amount of beginning parts that we need to make our final product, but that doesn't always happen. So, for example, ideally, when I make a s'more, I have 2 pieces of graham cracker. And by the way, that horrible drawing that you see, that brown square, that is a graham cracker. Ideally, I have 1 marshmallow and then 4 pieces of chocolate, and then I can make my like 1 s'more, right? So this is an example of a reaction. I have 2 reactants here, 1 reactant, and then 4 reactants to form 1 product. Okay, so in an ideal world, we have, 2 moles of crackers, 1 mole of marshmallows, 4 moles of chocolate to make 1 mole of s'mores. Okay, so I'm using the example of s'more instead of chemical compounds. But ideally, you have the exact coefficient that was used in your balanced equation. But that doesn't always happen. So sometimes my younger brother comes along and eats my graham cracker, so I don't have 2, I only have 1 graham cracker. Well, that's going to change the amount of s'mores I can make, right? Or maybe instead of 4 pieces of chocolate, I have 5 pieces of chocolate. And so sometimes we have extra reactants, okay, like this chocolate, and sometimes we have reactants that limit us from being able to make our s'more, from being able to make our product, and that would be the graham cracker, right? Because I don't have 2 graham crackers, and I need 2 graham crackers in order to make my s'more. So let's define these 2 terms here. You have limiting and you have excess. Your limiting reactant is the reactant that's completely used up, okay? It's basically the reactant that you don't have enough of. I can't keep doing this reaction unless I get more of it, okay? So it's the reactant that's totally used up, the one that we've basically run out of. The excess reactant is the reactant that is not fully used up. Basically, it's the extra reactant. So it's the thing we have extra of. So go ahead and write those definitions down for limiting and excess. So when we're looking at a problem, like example 1, and it says we have mercury and oxygen, and they form mercury oxide. They form this compound. The first thing I always do, remember, in any stoic problem, the first thing you do is you write the reaction and then you balance it, right? Well, it's written for us, so we don't have to worry about evening out charges. Notice that oxygen is written with the 2, right? That's because it's a diatomic. But it hasn't been balanced, so let's do that first. I see, for example, that I have 1 mercury on the left, and I also have 1 mercury on the right, so they're balanced. But my oxygens aren't. I have 2 on the left and 1 on the right. So if I put a 2 here, I now have 2 oxygens. But that also changed my mercuries, and so to get 2 mercuries on the reactant side, I put a big 2 there. So 2 to 1 to 2 are my mole ratios. So now that I look at this, I see I want 2 moles of mercury, and I want exactly 1 mole of oxygen to make exactly 2 moles of mercury oxide. Well, I'm not really given exact amounts, okay? I'm given 20 grams of mercury, and I'm given 5 grams of oxygen, and it's asking me which one am I going to run out of first? What's our limiting reactant? Are we going to run out of oxygen? Will that be our limiting reactant? Or are we going to run out of mercury? So these are kind of the 4 steps that I would recommend writing down, these 4 steps right here. These are the 4 steps that we follow in order to solve this problem. The first thing we're going to do is we're going to take our grams here of our reactants, and we're really going to have 2 problems. We're going to take grams of our mercury, and we're going to solve for how much product it would make. And then I'm going to take my grams of my other reactant, oxygen, and I'm going to solve for how much grams of product I can make. But the rule is you have to solve for the same product. In this equation, I only have 1 product. Mercury oxide is my 1 product. But sometimes you might see in other problems, you might see another product written here and another product written here. It doesn't matter which product you choose as long as you choose the same product. So the goal is here to solve for the same product. So it doesn't matter which one you choose, just choose any product and you're going to solve for how much product you can make. If you use 20 grams of mercury, then you're going to set up another problem where you solve for how many grams of product you can make using 5 grams of oxygen. So there's 2 problems, okay? So this is problem number 1, and then this is going to be problem number 2. We're going to see which one's going to produce the smallest amount of product. So if for example, let's say when we use 20 grams of mercury, we only produce 5 grams of our product, of HGO. But then in my second problem, when I do 5 grams of oxygen, maybe I produce 10 grams of my product. Well, that means oxygen produces more and mercury produces less. So mercury, I'm running out of. Mercury is my limiting reactant. So this kind of problem is neat because it's kind of 2 for 1. When you solve this way, not only do you solve for how much product you can actually produce, because remember, one of these we're going to have extra of. We're either going to have extra mercury or we're going to have extra oxygen. So we're really going to end up with 2 amounts. The one that produces the smallest amount is the amount of product I actually produce from this reaction. So you get to learn what's the limiting reactant, and you also get to learn how much product you can actually make. Okay, so let's set up our grams to grams T-chart. So the first one, we're in grams of mercury, and we want to go to grams of our product. Remember, whenever you're in grams, you first convert to moles. So we're going to go grams of mercury to moles of mercury. Then from moles of mercury, we can go to moles of our product. Our product is HGO. Then from moles of HGO, we can go into grams of H2O. So this is the mass. Okay, this is mass of our product. That's what we want to figure out. We're going to do the same problem down here for oxygen. So I'm going to set that up down here. We're going to be, instead of grams of mercury, we're going to start off in grams of oxygen, or O2. Then we can convert to moles of O2, because remember, whenever you're in grams, you want to convert to moles. Then from moles of O2, we can go to moles of our product. And remember, this is the same product. You always have to go to your same product. And then from moles of mercury oxide, we can go to grams of mercury oxide, which is, again, our mass of our product. So let's go ahead and set those up. The first one, grams of mercury goes on the top over 1. Okay, so I put 20 here, 20 grams of mercury. And then I'm going to, I have 1, 2, 3 conversion factors, right? And all I need to find are the conversions. So grams to moles is going to be my molar mass, and I'll write it over here. Remember, the molar mass in grams is equal to 1 mole. So we have, what's the molar mass of mercury? Well, I look on the periodic table right here, and the molar mass of mercury is 200.59 grams of mercury in 1 mole of mercury. So I'm going to put 1 there. So you see how this is, my grams are canceled, and now I'm in moles of mercury up here at the top. And then my next step is to go from moles of mercury to moles of HGO. And so my next conversion factor I'm using is moles of A to moles of B. Okay. And the numbers I'm going to use are going to be my coefficients. So I've already balanced my equation. So I kind of have to ask myself, how many moles of Hg are in how many moles of HGO? Well, I see there's 2 moles of Hg. I want that on the bottom because I want moles of Hg to cancel, right? And then up here at the top, I want moles of what I'm going to, right? Moles of B is what I'm going to. I'm going to moles of HGO because I wrote that up here. So how many moles of HGO I have? I have 2 moles of HGO, so 2 goes here. So now, lastly, I'm going moles to grams. And remember, I'm going to reuse this conversion factor right here to go from moles to grams. So 1 mole of HGO goes on the bottom so that my HGO can cancel. And where did I get the 1 from? Well, I got it from right here. It says 1 mole equals this many grams. So the 1 mole went on the bottom, and the grams is going to go on top. So what number do I put right here? Well, I have to calculate the molar mass of HGO to go on top. And so when I do that, I get 216.59 grams of HGO in 1 mole. So I'm left in grams of HCO, which is what I want, okay? And so I'm going to multiply all my numbers on the top. I'm going to multiply all my numbers on the bottom, and I divide those numbers, and you should get 86.4 grams. So what does this mean? This tells us how many grams of our product, how much we can make when we start with this many grams of mercury, okay? So now I'm going to set up my second problem. My second problem, I'm going to do grams of oxygen over 1, and I'm going to convert all the way to grams of my product. So how many grams of oxygen do I have? Well, it says I have 5.00 grams of oxygen, so that goes on top over 1. And then I have 1, 2, 3 conversion factors, okay? And I have to convert, I'm going to erase my arrows because you don't need those arrows now. So first step, go grams to moles. So grams to moles means we're going to use this conversion right here, the one at the very top. Remember, 1's always going to go next to this mole, so 1 goes there. And what goes on the bottom is the molar mass in grams. So what is the molar mass of oxygen? Remember, this is O2. It tells us right up here it's O2. So I have to find the molar mass of 2 oxygens. When I do that, it's 32 grams. So I'm out of grams of oxygen. I'm in moles of oxygen. So how do you go from moles of A, moles of one thing, to moles of something else, HGO? Well, I'm going to have to use this bottom conversion factor. And what do I put next to these question marks? Well, those are my coefficients, right? I remember I have I have 1 mole of oxygen. So oxygen's going to go on the bottom to cancel out. 1 mole of oxygen for every 2 moles, so 2 goes here, of HCO. And then lastly, I'm going to go moles to grams. So I put 1 mole of HCO on the bottom. Whenever you're doing molar mass, the number 1 is going to be at the bottom because it says 1 up here next to my conversion factor. And then the molar mass of HCO goes on the top, which happens to be the same molar mass as we had earlier, so it's still 216.59. Then I multiply my top numbers, I multiply my bottom numbers, I divide, and I end up with 67.7 grams of HGO. What that means is that for those 5 grams of oxygen that I started off with, if I use all 5 grams of oxygen, I would produce this much product. So now you really have to ask yourself this question. Which product is going to give you less? That's what it's asking. Which will give you less? We know that oxygen will run out first because it makes less product, okay? So oxygen is our limiting reactant. Oxygen, and I kind of wrote over the blank where you're supposed to put the answer. So oxygen is the limiting reactant, okay? Then the next question says, how much product will be actually formed? Well, ask yourself this question. Can we make 86.4 grams of mercury? We can't. Why can't we? Because oxygen, the amount of oxygen we're given right here, will only make us this much before we run out of oxygen. So we really can only make this much mercury. What's left over is mercury. We'll have a lot of mercury left over, but because we can't make 86 grams, we can only make 67 grams of our product.